can get through 2 handouts. So models, laws, and theories. Now I have to warn you, I normally do the second sheet first. Today I won't be. Okay, the second sheet, the reading level is a little bit easier. This one's a little more challenging. I'm going to read this one with you. Okay, so wave particle model of light, models, laws, and theories. So again, we're talking about models, laws, theories. Science is more than just a collection of facts and observations. Models, laws, theories, and evidence all play an important role in understanding the nature of science. And as I've maybe alluded to in the last few days, last week, I think the more and more citizens of the world that we have a better understanding of science, probably the better off we're all going to be. A scientific model is a conceptual representation or an idea in your head that stands for and helps explain other things. There's a wonderful definition of a scientific model. And I see that Jake is highlighting it, and others are going to follow along now that I've mentioned it. A scientific model is a conceptual representation or an idea in your head that stands for and helps explain other things. A good example is the globe sitting over there. It's a scientific model. I can take it out. It's not an idea, but it could be physical, right? It could be physical, a real thing. It could be imagined as well, or it could be even mathematical, right? A globe would be an example of a physical one. Imagine might be something that you've got in your head, obviously. Mathematical might be some sort of equation, maybe like F equals MA or something like that. Okay? In science, we develop models that have explanatory and predictive powers. In other words, they explain things and they also predict. Explanatory and predictive powers. And we test these models in the world around us. Okay, an example of predictive powers is the model of the universe. We can use the model of the universe or the model of the solar system to tell us where the planet should be in another month or 2 months or another year. And then we check and find out it may or may not be true. If our model predicts our observations, we accept the model as a valid description of our world. Give ourselves a little check mark and we say, yay, we're right. However, if our model encounters discrepant events, now I've already shown you a discrepant event last week. I think it was Tuesday. Anybody remember what discrepant event I might have shown you? No, last week, Joey. No. It was something very physical right in the room. The two black balls, exactly. I showed you a discrepant event because one bounced and the other did not. It didn't do what was expected. That's what the word discrepant means. Something happened that wasn't supposed to happen. However, if our model encounters discrepant events and fails to provide adequate explanations, we begin to modify our model or search for an entirely different model. Can you give me a very good example of a model that over the years has changed dramatically?
The solar system.
The solar system. Excellent choice. And actually, you're right about the periodic table, too. But I'll get to that one. I'll do it first. Periodic table was actually first organized by... Oh, my periodic table's gone. No, I wouldn't use it. But the periodic table was originally set up by atomic weight. And then they realized that atomic number was actually a better system. Okay? Was it Joey or Jay? Joey. Solar system model. Tell me how it's changed.
I don't know how to spread the curve.
Oh. Well, let's read ahead. Maybe that's just a good indication as to read ahead, maybe. A good example of a scientific model is the model of the solar system. At one time, it was thought that the sun revolved around the Earth on this geocentric model of the universe. Geocentric. What's at the center? Geo. Some Italian guy named Geo. Or a car, a really small car. No. The Earth at the center was considered to be a true representation for many centuries. The model encountered a discrepant event when the retrograde motion of the planets did not exactly fit the epicycles of the geocentric model. When did Mr. Bennett start speaking another language?
Yeah.
Exactly. What do you think retrograde motion is? Nicely done, George. Retrograde motion. The planets, and I'm sure that none of you are junior astronomers, if you were to watch the planets and sort of plot them for a couple of years, you would see that as the stars go across the sky, they tend to sort of go in a sort of a linear sort of, they're always here, and then they're to the right of that, and to the right of that. But the planets, they sort of wander. In fact, the word planets comes from the Greek word,
Planet which means wander.
something like that, planos, which means wander. Where'd you get that from?
Big Bang Theory.
You know, one of my finest achievements was one morning when a student came in to me and said, Mr. Bennett, did you see Big Bang last night? Of course, I said, of course. And they said, I got the part about, whatever. And I'm like, yes. I've educated my students to the point where they get the nerd jokes. You're right. Actually, I remember that episode now that you think of it.
It's a starry night in Greek evening.
Yeah. You find that for me and find me on YouTube so I can use it. Okay. Yes, it's teaching Penny and it's a starry night. You remember that one?
Oh, yeah.
Somebody find that for me. Post it. Okay. So yes, the planets are wanderers. The Greeks called them wanderers because they didn't go where they were supposed to. They would go along with the squad and then they back up. They do this little loop-de-loop kind of thing every once in a while, okay? Those are retrograde motions, and they didn't follow the model. A new model, the Copernican sun-centered model, named after Copernicus, Nicholas Copernicus, Danish, I believe. He provided a simple explanation of the movement of the planet, and it predicted the phases on Venus. He put the sun kind of at the center. You could do that at home. You need to listen to me. Okay? Copernicus put the sun at the center, and everything suddenly became simple. It's like, wow, that's so much easier. There was actually math nerds that had to figure out the planets would do these crazy, curly kind of things, and there was math nerds that had to figure out the equations for those kind of things. Yeah, oh my God, like, are you crazy? But they did it, but it was very complex. Copernicus said, put the sun at the center, and then guess what? It's a circle. It's easy. More or less a circle. Okay. What do I mean by the phases on Venus? What are the phases of the moon? How much is shown, right? You know, they got the new moon, right? Full moon, half moon, all that kind of stuff. Okay? Venus does the same thing. Copernicus' model predicted that. They got telescopes. They went, hey, Copernicus, you were right. We should keep this model. It works. Years later, the invention of the telescope permitted more sophisticated observations to confirm the predictions of the sun-centered model. And we adapted our model, and we now sort of agree upon it. Right? Okay. Observations can be used to test models, both externally or by thought experiments, as we rethink and apply our model to new and sometimes disruptive situations. Our observations can lead us to identify regularities and patterns in nature. We call these scientific laws. Scientific laws are things that we regularly see happen. For example, a simple scientific law would be what goes up must come down. We can also deduce laws given a certain set of conditions. For example, if light is a wave, we can geometrically show that the ratio of the sines and the angles of incidence and refraction is a constant. If you're interested, that's called Sine's law. Got nothing to do with sine, cosine, and tan. Oh, sorry, not Sine's law, Snell's law. Snell. No, it's not going to do that. Snell's law. Okay? Ohm's law for resistance, Charles' law, Newton's laws, all things that we have observed, and we regularly see them. Contrary to popular belief, laws are not absolute, but are often constrained to certain conditions. In other words, they only work in certain situations. Ohm's law is valid only for some materials, and our pressure laws are constrained by temperature. They're not true when the temperature is different. Even Newton's laws are valid only in terms of inertial frames of reference, and I'm not even going to get into that. Scientific theories form explanatory systems for phenomena and their corresponding laws, and may include presuppositions, models, facts, and laws. We know what those all are. What's a presupposition? Big fancy word for an assumption. Scientific theories form explanatory systems for phenomena. That is basically it. Scientific theories explain things. They're not guesses. They explain things. For example, Einstein's theories presuppose that the speed of light is constant in all frames of reference. Einstein's laws aren't worth nothing if you don't assume that the speed of light is a constant. Big Bang Theory, speed of light, constant. Anybody know the number?
Like 1 million meters per second.
Well, it's 3 times 10 to the 8 meters per second. That's pretty far. That's pretty fast. They only hold true for objects that are moving much more slowly than the speed of light. So Newton's laws only work when you're not traveling crazy super fast. We must be very careful with how we use the term theory, and I've talked about this lots. In everyday usage, the word theory often refers to an idea that is not proven. That, of course, is rubbish. Balderdash, exactly. In everyday, it's partially true that some theories, like many cosmological theories, are speculative ideas that are based on little evidence. Additionally, children often hold simple or naive theories about why things float or why the sky is blue. They explain them, they're just not very good explanations. Hypotheses or proposed solutions are often speculative, and we often seek to build support for them through predictions and observations. However, other theories, like theories of radiation, metabolism, or chemical bonding, have considerable evidential supports. Chemical bonding is a theory. A pretty darn good one. Okay? It is impossible to prove our theories for every possible case. But robust theories explain a great deal, and we sometimes literally bet our lives on them. Okay? Therefore, scientific theories lie along a spectrum from speculative hypotheses to robust explanatory systems. And I'd like you to, do you have a big spot at the bottom here? To draw something like that? Do you have a spot there? To kind of put an arrow? Oh, that's so good. Okay, I'd like you to put, right here, I'd like you to put robust. And here I'd like you to put the word speculative. Speculative means what? What does speculation mean?
Small guess.
A guess, you're not really sure. Little evidence. There's not much evidence, it's just kind of a guess. This is just the theory end. And as evidence is generated, we move into the robust territory. More evidence. Okay? And as theories move into the robust area, more and more scientists are in agreement. I did a little bit more research about that link that I showed you about the 95% of scientists believing that climate change is man-made activities are dealing with climate change. And it turns out there was a little bit of, there's some controversy over how they asked the question, and there's some controversy in how they categorize the question too. So there's always going to be controversy, right? You got to question everything, you got to read deep, and don't just sort of go by the headlines. Okay. So back to these theories here. For example, Bohr's model of the atom explains all the phenomena one might examine in an introductory chemistry program. More progressive theories require a more extensive background. You guys have seen the Bohr models, right? You know where you got the thing in the middle there, right? And then you pair up the electrons. Remember that stuff?
Yeah.
Completely false. But it's a good model for like grade 9, grade 10, beginning grade 11, but as you get into more and more chemistry, you actually find that the shells are actually, they're like subshells. Okay? Like the second one has got like 2 sub areas, and then the third one's got like 3. And then they kind of overlap a little bit, and it starts getting crazy. And one electron is going this way, and one electron is going that way, and it gets a whole lot more complicated.
So why would it be just something that's wrong?
It's not so much that it's wrong, it's that it's good enough for what we're trying to teach you. Okay? It's still got some validity for that particular purpose. Okay? We're speaking a language that you can understand. Okay? While it's important that our understanding of the nature of science is embedded in the context that the world is rational and can be understood, we never really know if we've achieved the most rational explanation. There's always going to be room for some improvement. In science, the truth is elusive, but our beliefs must extend far beyond individual opinions. In science, we must exist on evidential argument. Okay, I lost Margot here. One of the main questions scientists are concerned with is the relationship between theory and evidence. It's not unusual in science education to make a knowledge claim in the form of "I know that." For example, while discussing health with your doctor, she might say that lowering cholesterol level lowers one's risk of heart disease. To further the claim, support is found for that knowledge claim. We call this support evidence. The nature of the evidence presented will depend upon the background knowledge of the knowledge claimer, in this case the doctor. For example, she might stress the statistical evidence or discuss the latest hypothesis of the underlying mechanisms that relate cholesterol level and platelet formation. Of course, one might simply quote a recognized authority, like the Department of Health, and not attempt to formulate an argument at all. Okay, you might go see the doctor about something, and she might just say, you know what, just get your cholesterol down. Trust me. Or she might refer to the health department wants me to do this. Or she might go into a big long theory kind of thing, right? It also depends on what you know, right? The doctor's going to speak to a 10-year-old a little differently than the parent of that 10-year-old, and especially if that parent of the 10-year-old happens to be a physician. They're going to speak to you differently. Since the background knowledge of the claimer and the intended audience may be different, an evidential argument must be given that makes sense to the audience, connects with their prior knowledge and experience. Doesn't talk above their head. Okay? Teachers have to be aware of this all the time. We can't talk about kids' heads. Consequently, a selection process or theory choice is involved in deciding the adequacy of a given theory in terms of its ability to accommodate the available evidence. And you can see what I'm talking about, the reading level here. It's your brain's starting to go, what is he saying, right? I know that. Yeah, I do. I'm trying to make it simple for you. This selection process reviews and judges the characteristic of a good scientific theory. A good theory is accurate. That's something you need to know. You got to be accurate. Predictions the theory you make must closely match the observations to support the theory. If you make a prediction and then what you actually observe is pretty close to that, that's accuracy. However, accuracy is not the only characteristic of good theory. When two theories are equally accurate, the better theory is often the simpler one. And that, my friends, is known as the law of parsimony. I write sideways. The law of parsimony. And I have a beautiful handout there. It's on the back. We'll get to it probably tomorrow about the law of parsimony. And about a horse that does math. Everybody loves horses that do math, right?
Yeah.
No, yeah. So here's another example. The Copernican model of the solar system was no more accurate than the Ptolemaic model. Copernicus was just as accurate. The math nerds had all those curly-Q retrograde things all figured out. It was just crazy math, right? Series of epicycles to account for the motion of planets. In the face of equally accurate models, Copernicus' theory simplified the model of the solar system. Circles. Furthermore, a good scientific theory has explanatory powers that cover a broad scope. It explains a lot of things. It explains a lot, even phenomena that it was not intended to explain. You inadvertently explain something they never thought of. The scope of a good theory also extends to bold predictions. Often these predictions, such as Einstein's predictions that light would bend near large bodies, not confirmed until years later. Okay, so sometimes that happens. You explain things that you can't confirm yet. You have to wait for the technology to catch up. And that is all. Oh. Wow, that's crazy, eh? Yeah, that is rubbish. How do I do that? How do I get rid of that now?